Okay, welcome back everyone to this tutorial series on the theory of computation. So in this very first set of slides, I'll be talking about the mathematical preliminaries required to understand the new concepts that are going to be introduced throughout this topic. A note, though, about this set of slides is that it's not going to be exhaustive. So that just means that there are some things that I will certainly miss in these first set of slides that um, might be necessary. So there's going to be some mathematical concepts that I'm going to miss in these first set of slides that you'll probably need in the future. So for instance, equivalence relations. But for anything like that, I'll introduce the sort of mathematical notion right before I introduce the new topic. So you don't have to worry too much about that. Okay, with that being said, let's actually get to some material. So I've already done introductions in a previous video. So let's go over some review of set theory. So the first thing you need to do to review set theory is to define what a set is. So for the purposes of this tutorial and for the sake of practical exercises, I'm going to define a set S as some unordered, well-defined collection of distinct elements. So there's a couple ways of creating or defining a set by writing it down. So the first way of creating or writing down a set is using explicit notation. So you can see in these first two examples here, I've created a set using these curly braces, and inside the sets, so for instance, inside set S sub 1, you have some numbers, a string, some symbols. So this is just trying to show you that a set is a collection of objects or elements, and those objects or elements can be anything, even sets. Okay, so in S2 we have this dot 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 notation, which tries to create a more compact version of the set, but this is just to say that this set is the set of natural numbers from 1 to 49. The other thing is that sets are collection of distinct elements. So elements in a set will be unique. So for instance, in this set here, you're not going to have the element 2 twice. It's just going to be there once. Okay? Then there's another way of defining a set or creating a set using natural language. So when you use natural language, you try to describe the property of the elements in the set. So for instance, here I have S2 is the set of elements n, where, so you can read this two dots as where n is an integer greater than 23. So that means that this set starts at 24 and then keeps going, right? So there isn't a final number to this set. This is actually an infinite set. Okay, in S3, S3 uses another way of creating a set. It uses the set builder notation. So in the set builder notation, instead of just using natural language, I'm going to use some well-defined mathematical properties that showcase the description of my elements in for instance, S3. So here my set is S3, and the set S3 contains elements n in the set of natural numbers. So Z, as a reminder, is the set of natural numbers. And this is the description of the elements in my set. So my elements are going to be greater or equal to 0, so non-negative, and they're going to look like something times 2. So here, this k, you can also think of k, this should have been specified, that k also belongs to the integer. So my element is non-negative, and it looks like 2 times something. So what does that mean? That means that, if you remember from your discrete math class, that this is actually an infinite set of non-negative even numbers, right? So if you take any even number like 8, then you know that 8 is greater or equal to 0, so that's good. And 8 can be represented as 2 times 4. So that means that it fits the description of my set builder notation, and so it's going to belong to S3. Okay? And then similarly, actually, if we go straight to example 6, so this is another example of set builder notation where I have that my elements look like n cubed minus 3, where n belongs to the set of integers and n is from 0 to 27. So here I have an extra question here. What's the smallest number in this set? Well, here the smallest number is going to be the smallest number in this range, right? So it's going to be 0 cubed minus 3, which is minus 3. And I'm able to write this down because I know that n goes, so n here goes from 0 to 27. And because n, right, because my integer is restricted from 0 to 27, this restriction forces it to be a finite set of elements. Okay, and lastly, just a reminder, n, right, the set n is the set of natural numbers, right? So this is the set of natural numbers, okay, which it depends who you ask. So if you ask a pure mathematician, this might start at 1, 2, but then if you ask a computer scientist, it might start at 0, okay? Then the set z is the set of all integers, so integers. Q is the set of rational numbers, so any number that can be represented as P over Q, where P and Q are both in Z. And then R is the set of real numbers, which not only includes the set of rational numbers, but also includes the set of irrational numbers. So for instance, the square root of 2 is an R. And so from your discrete math course, you'll probably remember that there's a very nice proof that shows that square root of 2 is in the real numbers. And that's in fact because it's irrational. Okay, so now we know what a set is. The next thing that we need to know about sets is set membership. So if an element A belongs to a set A, then we write A belongs to A, right? So little a belongs to big A. Otherwise, we write little a does not belong to big A. Okay, so let's look at an example. Here I have the set A1. A1 is the set of integers from 1 to 75. Okay, so is 2 in A1? Well, yes, 2 is in A1, it's right there, right? But if you look at minus 45, minus 45 is outside the range of A1, and so it does not belong to A1. Okay, this example here, I'll let you do as an exercise, but I think in terms of set membership, this idea is quite straightforward. And this is just an extra example for you to practice with, just to make sure that this concept is well engraved in your head. Okay, the next concept I want to talk about is the notion of subsets. So a set A is a subset of B if every element in A is also in B. Okay, so in other words, and this can be written as A and then subset. So this is the subset notation B. So in other words, if I want to write B in terms of set builder notation, right? Then B, A is a subset, right? So A is a subset of B if for every A in A, right? A is also in B. So this is the more mathematically rigorous definition of a subset using the universal quantifier. So A subset B is equivalent to saying that for every element A, little a in big A, little a is in big B. Okay? So for instance here, I have the same set, right? So this is actually a particular case of subset. If this is my set A, and this is also my set A, then A is of course a subset of itself, right? But if I had a more complicated, so a less obvious option, so if I had 1, 2, so the set containing the elements 1 and 2 is a subset of the set containing the elements 1, 2, 3, because every element in this set, so 1 belongs to this set, 2 belongs to this set. And so the set on the left-hand side is a subset of the set on the right-hand side. Okay. So then another question here is it true that the set of natural numbers is a subset of the set of integers? Well, of course, take any natural number, it's going to be an integer, right? However, if you look at the set of real numbers, the set of real numbers is not a subset of the set of integers because specifically of the case I talked about last time, so in the last slide. So if I take square root of 2, then I know that square root of 2 belongs to R because it's irrational, but because I know that it's irrational, right, the square root of 2 is not going to be in Z. Okay, and then there's a stricter notion of a subset, which is a proper subset. So set A is a proper subset of the set B if every element in A is also in B, and I have this extra restriction that the set A cannot equal the set B. And so we write that as A is a proper subset of B. So then, for instance, in this scenario here, A cannot be a proper subset of itself. But here, because I have this as A and this as B, because all of my elements in A are in B and A is not B, then in this first example, I do have a proper subset. Okay, and then the next example I'll also leave to you as an exercise, just to practice the notion of what it means for something to be a subset versus a proper subset. Okay, the next idea that's very important to talk about is the notion of an empty set. Okay, so students often say this. They say that, oh, you take nothing and that's the empty set. So the empty set is not nothing, okay? The empty set is a set. Namely, it's the set that does not, right? It's the set that does not contain any elements. And in fact, it's the unique set that does not contain any elements. And that's why it's so important. So for instance, here, I have in set builder notation, I'm saying that my set here, A, is the set of elements N, where N, so let's say N belongs to Z, just to be more specific, N is greater or equal to 0, and N is less than 0. Well, there is no integer N that satisfies this property, right? And so this means that A equivalently is also the empty set. And a very important property of the empty set is that the empty set, so if we look at example 3, the empty set is a subset of any set. Right? So this is definitely true. Why is this true? So why is, if you take any set A, then the empty set is going to be a subset of A. Well, because this is vacuously true based on the definition of a subset, right? So, what's the definition of a subset, right? It's that for every element x in x, x is also in y, right? So x subset y is equivalent to this definition, okay? But now, if I replace x with the empty set, right? For every element x in the empty set, well, there are no elements in the empty set, right? So of course, if there are no elements in the empty set, then this next statement is vacuously true, right? It's immediately true because there is nothing to check in y. Okay, there is no element in x for which you have to ensure that x is also in y. Okay, and so the empty set is a subset of any set. The next idea is the universal set. So the universal set is the set that contains all elements in the context of your problem. So usually in the context of theory of computation, theoretical CS, it's usually very clear what the universal set is. Typically, that's because in this sort of topic, what you usually how you usually write down a set is, you know, the set A is equal to x in, let's say, the universe, such that x and then some condition, x some condition. Okay, and so clearly the universal set is going to be U. Okay, and so there's not going to be this tricky issue of knowing what the universal set is in a given scenario. Okay, um, so the next idea is the idea of power sets. Okay, so what's a power set? Well, if you have a set S, so given a set S, then its power set, which is either in 2 to the S or just P of S. P of S is the set, right? So P of S is a set of all subsets of S, right? So P of S is a set of all subsets of S. So if you want to write this more formally, right, then you could say that P of S is equal to X such that X is a subset of S. Okay? So, well, what does this actually mean, right? This means that every element in P of S is actually a set, right? So if you wanted to know the type of the element in that set, it would be a set, right? So I know I just said set many times in a row. Let's actually look at an example to make this a bit more concrete. So I have the set S, let's say, is the set A, B, C. Okay. Now I want to know what the power set of S is. Well, the power set of S is going to be the set A, right? Because every element in the set, let's just call this big A, every element in the set big A, namely just little a, is going to be in the larger set S, right? And so the same thing is true for all the other singleton sets, right? And then I do the same thing for all pairs, right? So for AB, for AC, and then for BC, right? So these other sets are also all subsets of S. And then I also have the set S itself, right? Because we're not dealing with proper sets, we're dealing with only subsets. Okay, so now am I done? No, right? Because I'm missing the element that's the set that's a subset of all sets, which is the empty set. And so, in fact, whenever you write power set of a set, it's always going to contain the empty set, right? So for instance, if I were to ask what the power set of the empty set was, well, this is going to contain, right, the set, the power set of the empty set is going to be just the set containing the empty set, okay? Because the only set that's a subset of the empty set is itself, right? And then finally, again, example 3, I'll leave it as an exercise. I don't want to sort of belabor these examples because otherwise this video gets very long. I'm just trying to give you quick reminders of what these concepts mean. Okay, and finally, before we get to set operations, I want to talk about one, right? Yes. I want to talk about one final concept, which is the notion of cardinality. So the cardinality of S, which is denoted 2 vertical bars between which you have your set, is the number of elements in the set S, right? So you can think of it as the count or the length of your set. So for instance, here I have my set 1, 2, 3, 4. This set contains 4 elements, so the cardinality is 4. The next, okay, so maybe let's do this one because it's interesting. So for example, 2, how many elements does my set S have? Well, it has 1 element, 2 elements, 3 elements, and then all of this, right? So I have 1 comma here and another comma here. So this just counts as 1 element, right? Even though it's a set, the cardinality of S is still 4 because it contains 4 elements. Okay. So if S is finite, what is the size? What is the cardinality of the power set of S? I won't give you the answer to this one, right? But I want you to think about the possibilities. So let's say I have a set S, which is 1, 2, 3, 4. Okay. So I want to count the number of elements in P of S, right? So how many elements does P of S have? Okay. Well, I know that P of S contains sets that are subsets of S. And so if I try to start generating all of the subsets of S, what I can think of is I can think of the fact that I can ask for each element in S, right? So I can ask for each element in S, is it in the subset or not? So I have a yes, no question. I have a binary answer to this question. So either 0, 1 is not going to be in my subset, or 1, 1 is going to be in my subset, right? And so it's the same case for the next 3 elements. So I see that for each element, I have 2 choices, right? So I'll let you, based on the fact that for each element, 2 choices are available, right? So either is it in the subset or is it not in the subset? And so I'll let you use some combinatorics, some counting to try to think about then what the size of the power set of S will be. So we've been talking about finite sets for now. The next thing is what happens when you have an infinite set. So in the case of having an infinite set, your set is either going to be countably infinite or uncountably infinite. So I won't belabor this point a lot, I won't go into details, but I'll just remind you that countable infinity is when there's a mapping from, say, this infinite set to the set of natural numbers, okay? Uncountable infinite, so an uncountable infinity is when this isn't possible. And so that's when you get into the real numbers and things like that. But I won't go into too much detail about cardinality here. Okay, so I think I'm going to stop this video here. And in the next one, we're going to talk about set operations.